I have refilmed this more times than I want to, but I'm going to try to do this again and see if this finally works. Alright, anywho, let's do a fairly comprehensive review on acids and bases. So first, what is an acid? What is a base? We have three major types of acids and bases that are covered. We have the Arrhenius, the Bronsted-Lowry, and we have the Lewis. So the Arrhenius definition has to do with aqueous solutions. So this is specifically to being in water. This has to deal with what happens with protons for Bronsted-Lowry, and this has to do with electrons for Lewis. Maybe you remember your Lewis structures dealing with like electron dots and a bunch of stuff like that. So Lewis and electrons tends to stick in your head a little bit. Alright, so an Arrhenius acid is something that when it is in solution with water, it forms H3O+, whereas bases will form OH-. This can be limiting in cases where we're not dealing with water. Perhaps we are adding sulfuric acid, nitric acid together where water is not present. In cases like that, nitric acid will function as a base. But nitric acid being a base? Yeah, the Arrhenius definition does not cover that. So Arrhenius is very specific with water. And this is where the notion of the pH of 7 being neutral, because things are done in water. So a pH that is less than 7 is acidic compared to water, and a pH that is greater than 7 is basic compared to water. Moving on to Bronsted-Lowry. Let's just leave it as it is. So Bronsted-Lowry, we are looking at the acceptance and donation of protons. An acid is a proton donor. So maybe we think of something like HCl. You know, I'm going to make it more generic. Some generic acid, HA, is donating off a proton for something else to grab. So here we have a proton donor. Whereas for bases, we would be accepting protons. So maybe we have a proton present. Maybe we have a base present. So it will absorb that proton, and we get the conjugate acid. So this is a proton acceptor. If you forget these, you can think of a very general case of these. If you have H3O+ or H+, these are sources of protons. In fact, H3O+ is just water with an extra H on it. That gives that water a positive charge. So it wants to give up a proton. Acids are proton donors. Think of the very generic base from the Arrhenius definition, hydroxide. This is negatively charged. It'd be happy to accept a proton. So here we can accept that proton. We can take it in and form water. Whereas here, some base will gladly grab that H, or you can draw it grabbing that H. So here we have protons being donated. The Lewis definition now deals with electrons. And actually the arrows I drew are showing the electron flow. So you see the acid, the H+ or H3O+, is accepting electrons. So this is an electron acceptor. Whereas the base is giving up its electrons. It tends to have negative or neutral charges. It wants to give up those electrons to grab onto a proton. So these are electron donors. And it should make sense that we see opposites here. Something that it donates protons can accept electrons, because if it can donate a positive charge, it can accept a negative charge. Okay, cool. So let's look at an equilibrium equation. To keep things simple, I'm going to say a generic acid is in the presence of water and breaking down, or I should say dissociating, in H3O plus and a minus. If you were to write out the equilibrium equation for this, we would say that K, the equilibrium constant, for an acid, because we have an acid dissociating, so we'll say Ka is equal to the product side divided by the reactant side. If you have done anything with equilibrium constants so far, you'll be familiar with this. The reason why water is not included is because you don't include liquids or solids in these equations. You focus on things that are either under pressure, like gases, or have specific concentrations, like aqueous solutions. So maybe you look at the concentration of your acid or its conjugate base. But you don't care about water, you don't care about solids. Now there is a huge array of different reactivities with atoms, so much that trying to model out this reactivity leads to some issues unless we deal with logarithms. Logarithms allow us to see orders of magnitude as opposed to exponentially growing scales. If you were to try to graph something that very quickly goes off towards infinity, it might be very hard to get a good grasp of any of this. Maybe when it's at 1, it's at 10. Maybe when it's at 2, it's at 100. And it's at 3, it's at 1,000. This graph goes off like crazy. So cue logarithms. So here these just increase, and a logarithm makes something nice, pretty, and linear. That's the kind of thing we see here with acids and bases. K values can range massively. You can have Ks that are huge that you do with strong acids. So strong, in fact, that don't even give it Ka values because you're effectively dividing by 0. To being incredibly small, like things that aren't very soluble at all, stuff that doesn't want to dissociate. Perhaps you're looking at methane. This is an organic molecule. Oops, that's not methane. You know what? That's fine. You're looking at methane. How likely is it to give up that proton? It's not. So it would have a very, 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 very tiny Ka value. So you have a huge range of different values arise in this. And it makes sense to want to use a logarithm. So let's utilize some logarithms. Anytime that you do the log of something, now mind you, these are almost always small numbers. We deal with when you divide stuff out, it's always something over the total. This is how we look at concentrations, percents, and so forth. So generally, this number is going to be small. It totally depends on the units, but oftentimes it's way less than 1. For that reason, if we just did a straight logarithm, like the log of Ka, we're going to be getting negative values because they tend to be very small. If we did the log of H+, we're going to be getting negative values for that. No one wants to deal with negatives, so we can deal with positives. So we have defined a definition saying the negative log of Ka is going to be pKa, the negative log of H+ is going to be pH, and we can take this even further. So like the negative log of Kb is pKb, the negative log of OH is POH. You can do the negative log of Kw, which is pKw. And we can keep going. If you do the negative log of something, it's the power of that something. You're looking for its exponent. That's the whole point of this. Logarithms look for exponents. All right, so let's apply negative logs onto this expression. So we have the negative log of Ka equals the negative log of H3O plus A minus over HA. I'm writing it like this just for simplicity because of my next step. You can split logarithms into multiple logarithms. For example, if we have log AB, this is log A plus log B. So if I had the negative log of AB, this is just the negative log of A and the negative log of B. That's exactly what we're going to do. So we have the negative log of Ka. We have the negative log of H plus, H3O plus. And we have the negative log of A minus over HA. Now we can substitute in what these represent. So the negative log of Ka is pKa. The negative log of H3O plus is pH. And the last part just stays behind, A minus over HA. This is called the Henderson-Hasselbalch equation. Generally, when you see this expression, it will be written out as pH equals pKa plus the log of A minus over HA. This is the Henderson-Hasselbalch equation. It has lots of usefulness when you're dealing with producing buffer solutions, or if you're dealing very exclusively with pH and pKa. You can use it for H's and Ka's, but this is after you've already applied logarithms to the expression, so it tends to make it a bit easier to deal with. We can also do a base equation. So if we have a generic base that's reacting with water, we will see this form HB plus, let me make that look a little bit better, plus OH minus. So our Kb is going to be equal to HB plus OH minus over B. Again, you exclude water. Now we see that this looks very similar to what we did up above, except now instead of it being Ka, we have Kb. Instead of having H plus, we have OH minus. And instead of having, oh, I didn't write it this way, well, I'm going to. This guy is a conjugate base, this guy is a conjugate acid. Let's talk about that real quick, then we can come back. If you have a situation where you have, let's say, HA reacting with B to form A minus and B HB plus, what can we call these? So focusing on the reactant side, this is an acid. It is going to be donating its proton. I wrote that as a plus, this should be a minus. There we go. This will be donating its proton, this will be accepting a proton, so this is the base. So these will turn into conjugates of whatever you started with. So the conjugate of an acid is a base. So this is the conjugate base of this acid. And this base will turn into its conjugate acid. So acids become bases, bases become acids. You can see from the other perspective that even though this is what wanted to donate a proton, the HA was donating a proton, on the reverse side, it's HB that's donating the proton. So our acids have flipped. One has the A on one side, one has the B on the other. An acid becomes its conjugate base, a base becomes its conjugate acid. So now on to my other form of writing this. I will write this log of base over acid. So the Henderson-Hasselbalch equation can be expressed as pH equals pKa plus log base over acid. So then coming here, I see that this is acid over base. So everything here has been flipped around. So going through the same derivations we did up above, and just skipping to the end, I get pKb, or almost skipping to the end, equals POH minus the log of acid over base. That's HB plus over B. And resolving this, I get POH equals pKb plus log acid over base. So here is a base version of the Henderson-Hasselbalch equation. We almost never see this in a class, but it can be very useful. You can also manipulate these other expressions that we have up above. I'm going to do it starting here. We can take this equation and let me just rewrite it here at the bottom. Ka equals H3O plus A minus over HA. And let's say we wanted to solve for H3O plus. So H3O plus equals Ka times HA over A minus. So from this expression, I can see that H plus is equal to our constant times acid over base, whereas for the Henderson-Hasselbalch, pH equals pKa plus log base over acid. So notice that last term gets flipped, but these are the same expression, just one has a logarithm applied to it, one does not. We can do the same thing with the base, so I get the concentration of OH minus equals Kb times base over acid. So what have I observed from this? If you're dealing with the Henderson-Hasselbalch equation, whether it be its acid or its base form, OH corresponds with pKb. But then your logarithm is acid over base. It's flipped. But when you deal with its pre-logarithm, they all match. We have base, base, base. So the logarithm ends up flipping that last term. The reason why is because a negative log was involved in this, and a negative in front of a logarithm flips what's inside of it. For example, the negative log of 2 is the same thing as 1 over 2, or log 1 over 2. Because we use a negative log on both sides to switch from here to here, the things inside the logarithm will flip. So instead of having base over acid, we end up getting acid over base, simply because it was negative. Okay. Onwards we go. So far we have seen various equations to relate these together. We get the concept of acids and bases being Arrhenius. Let's just go back to the top. The Arrhenius acids and bases, where they produce H3O plus or H minus in solution. We have the Bronsted-Lowry acids and bases, where they are proton donors or acceptors. And the Lewis acids and bases, which are electron acceptors, electron donors. Mind you, when you get to organic chemistry, these end up being called electrophiles and nucleophiles. And they no longer have to do with only protons and electrons. They can be, that you can do these with all other solutions, and it makes up like 99% of organic chemistry. Once you get good at identifying acids and bases, you can extrapolate that information and get fairly good at doing electrophiles and nucleophiles. And once you get really good at that, the majority of organic chemistry will come naturally to you. If you struggle with acids and bases, unfortunately, it will come back at you in organic chemistry to an extent. There's lots of patterns there that can help you out, but these are very related concepts. Okay, so then we wrote out an expression here showing how acids become their conjugate base and bases become their conjugate acids. Here was an acid dissociation expression, and then showing its equilibrium constant Ka, as well as a bunch of derivations on the right side that you kind of need to know. Negative log of something is the power, the p of it. So then I did the negative log of both sides of our equilibrium expression to solve for the Henderson-Hasselbalch equation. But you can also not run it through a logarithm and solve for this other form. So you have the Henderson-Hasselbalch form, which is a logarithmic form, and a non-logarithmic form, which is just a manipulated version of the equilibrium equation. We do the same thing with bases, and we end up with the same situation, just everything gets flipped. H's become OH's, Ka's become KB's, base over acid becomes acid over base, and base over acid, I already said that one. Okay, so the base over acid here becomes the acid over base here. And for the other expression, it's acid over base becomes a base over acid. So those end up getting flipped. Now let's look at more math. So that's useful, but how do you switch between pHs and POHs? There's got to be some relationship between the two, since acids and bases react with each other.